one thing. No, it's been a good quarter semester or whatever. So I mean, I thought you guys all did pretty well in here. I mean, it's kind of anyway. The last question on the homework is some kind of assessment thing. So like just the format's changed a lot in here. So like maybe if you learned anything, and then like just some comments, doesn't matter if it's plus or minus. The undergrads, if you're senior, I mean, the rule used to be, and I think it still is officially, that if you're a senior, you don't have to take finals, So this last homework is kind of a final. So unless you want to, I mean, you can do it, so, but anyway, it'd be good if you could answer F, from an undergrad perspective, it'd be useful. I don't know, maybe you guys could say like how to get more undergrads. Like it's set up to be like a grad course for materials for the qualifier prep kind of thing. So it's just kind of hard to change the format much, So we're somewhat stuck with it. We used to have a class for undergrads like this. Joel Fried used to teach a Polymer undergrad class, and he wrote a book that's a good book. It's actually on the webpage. I think it's under Fried or something. He moved to Louisville to become like head of chemical and then provost or something. And now I think he's back at UC doing something like in the college, but he's still around. But that book's a pretty good book. I mean, it's kind of like chemical engineering, polymer mixture of stuff. It's got some of what's in this class and some other things. Anyway, probably we're getting 2 more polymer guys and materials that come the fall. So that's good. 2 young guys. One guy's from Kentucky. He's been doing like surface things, adhesives. And the other guy is Ben Yevitt, who's like he's been working in this area that the quiz is about. So like this paper, like this guy Yevitt, but there's one paper that's on the webpage, I think, that he's the first author on. He did a postdoc with this guy Koga at Stony Brook, who does dynamics measurements using X-rays and neutrons. And before that, he worked with Winter at UMass. So he's a pretty good guy. He'll be like faculty in materials. He'll probably teach some classes too. He's a rheologist, I guess, mostly. So he does PhD with Winter, who's a rheologist. But then this guy Koga, who did a postdoc with, is a scattering person. So it's kind of like a mixture between scattering and it's a characterization mostly. Anyway, so he's there. So there was room for more classes, some like this intro to polymer that Euro teaches. There's this class, this characterization. I think Yavitt said he wanted to teach characterization, which I taught. I mean, it's still enlisted teaching, but I haven't taught it since COVID because it's kind of an in-person class. Like it's a lab class, and it also like it's rare that undergrads take that because it's like a lab. It's like a PChem lab class, so it's a lab a week, and the labs are 25 pages or 30 pages, so it's a lot of work. Yeah, so everyone drops.
That's like a one a semester kind of like you take. Okay.
I mean, people say it's the course they learn the most of their whole career. You see, but basically, it's a lot of work. It's a lot of work to do it too, because you have to grade all these lab reports.
I pretty need a TA.
Yeah, but they can't grade. They can't do that because still teach grad students how to write. You can't have a TA do that. It's not like ABC. Red or white or whatever. So. Anyway, maybe Yavitt will probably teach that class, so that would be good, to take it off me. But so anyway, this I don't know what else. Anyway, I'm pretty happy with the way it went, except the student population was high enough. And then also like if this kind of hybrid format thing, whatever I've been doing, where I record it, like if that makes sense or. I think it's pretty good, because you can just watch it later on if you want. I mean, we don't get a huge crowd in the classroom sometimes, but that's okay. I mean, during COVID, it was just me, you know, so it was like one or two is okay. So I don't really mind that. And we've had a lot of feedback and stuff in here too. So it's been pretty good, I think. I'm pretty happy with it. You know, in the past, it was like a quiz a week and I'd give you this thing, basically the same thing blind. Yeah, so there'd be, so 2 people would get an A. 2 people out of 30 would get like straight A. They'd smoke it, you know. And then probably 5 or 8 out of 30 would like we used to have 30 in this class. And then 5 or 8 would be like struggling, you know, really bad. And then some in the middle would be kind of getting a B. So this way, everyone's getting an A, but I think hopefully everyone's learning something too, because at the bottom, whatever 5 or 8 learned nothing, you know, and the top 2 learned a whole lot, and then the middle kind of weren't that happy. I mean, they're like struggling. They learned a lot, but they didn't kind of realize it. Maybe. Okay, hopefully, this kind of group thing. The idea is that you can kind of see how the top people work, you know, so you can see like what they're putting in and what they're getting out. And then it evens it out a little bit and it makes it a little bit more so like you're working as a team, which is what you need to do anyway. Like working on your own, it's possible to do that, you know, but it's not very fun for one thing. Actually, you're going to really need to rely on other people, especially these days. So it's kind of like useful to kind of have this team thing going. And the grades, I don't really care about anymore. I never really cared about them, but basically now I really don't care about it. You know, so it's like,
I mean, especially for like grad students, it's like,
yeah, for
it
grad
doesn't matter
students, it's
that much to
stupid.
us.
No one even looks at the grades. It's just your dissertation for grad students, or
Yeah.
your thesis, or master's or PhD. So anyway, whatever.
And seniors, I mean, if you're gonna have a job.
Yeah,
it doesn't
seniors
really
is
matter.
just, it should just be to boost your grade if you're taking an elective, the way I see it. So it's not like something, like the core, like when I teach thermo, it's kind of brutal. But I mean, that's different because it's a required class. And it's kind of like you should know that stuff somewhat, you know. This is more like icing on the cake. So if you don't get it right, it doesn't matter that much. So. Anyway, so this thing, this is a little bit complex. I showed you this thing, right? This McKay thing. And this is 2006. So things are kind of progressing along here. Now, 2006, McKay publishes this thing. It's one of the first papers. This has 1,200 citations. And it's like the particles, he says they have van der Waals interactions, which only operate over short ranges. That allows him to say, like, he just has this little part. So big particles don't have as much of that as little particles. That's why little particles kind of work better or something. That's kind of his argument, more or less, right? So then there's people that do thin film. So like you can coat a polymer into a thin film and measure the glass transition. It turns out the glass transition shifts. You know, and there's also the bound rubber people from Carbon Black who said like the carbon goes into the tire, then there's this layer of confined polymer around it, right? And the higher the loading, the more fraction of the tire is made up of that interfacial part, which has a different TG and has different dynamic properties, different relaxation time. So basically, the change in the tire, there's one school of thought that it's all just that interface. So the whole thing is just an interface, and then that's why the properties change. That's why you have the filler, right? So there's kind of different schools. One of these, I think it's this paper, he goes through kind of what can happen depending on how the affinity of the particles to each other and particles to the polymer. So they can so if you get a lot of affinity between the particles and the polymer will like kind of crystallize on the surface. And you can get these, see the little red beads here? So those are like surface binding, like glue between the particles. And that's what this paper this week is about, is that glue. So that's where the energy, the NP energy, so nanoparticle polymer energy, attractive energy is high, super high, right? So it's just going to go right to the surface. Then as you reduce that, then the particles don't like the polymer, then they'll clump up, or you get this intermediate one, which is the other paper saying is the good one, like you're dispersing. right? So this groups that are just studying this high interaction energy, and the polymer that you look at for that is this poly 2 vinyl pyrrolidone. Don't work for this guy. And so this thing and silica just like each other a lot. Somehow the hydroxyls in the silica and this thing, hydrogen bond or something. There's some kind of ionic interaction. So this is the glue thing, like it's the glue model. It's this one. Right? So there's a whole bunch of papers, including this one, where they're doing poly 2 vinyl pyrrolidone and then silica nanocomposites. And that's a whole subcategory of these things. So it's not a commercial material. That's right. So it's kind of like something that's useful to study because it's going to fit in with this scheme of things. So that was there's that McKay thing, and then this is this paper. So this is showing how they think this works. So this is Schweitzer. Okay, Schweitzer was at Sandia National Lab and worked with a guy named Kuro, and they came up with a thing called Prism. It's here somewhere. So there's this paper by this guy Tyler Martin at NIST, who's like a young scientist, does simulations. He did his PhD with Arthi J. Raman at Delaware, originally at Colorado, and she moved there. Anyway, he moved to NIST, and he's doing kind of what J. Raman does. So he's taken that pie of Schweitzer and Kuro, and he's made it into a package, more accessible package or something. It's Pi Prism. So I think it's Python Prism. And it basically you put in the information about the polymers, and it comes out with a correlation function. And it can also give you the chi parameter and some other stuff. He listed it here. I thought this was pretty low level discussion of it, because if you look at the Schweitzer and Kuro papers from '86, it's a long time ago. But when they did it, this was like the hottest thing, like the latest hit radio song, whatever, So, and it's continued on. So Schweitzer still puts Prism into everything he does. So he's going to look at nanoparticles. He's got this hammer. Oh, that must be a nail. So he's going to use Prism to get this correlation function. And then once he gets the correlation function, he's going to use that to talk about these. So this is a correlation function between particles in a polymer mixture. And then as you increase the composition of the particles to 6%, 16, 33, you get a monolayer. So the one sigma is the beads on the polymer, and then D is the diameter of the nanoparticles, and D is 10 times sigma. Okay, so that's the scheme he uses throughout this. So when he goes to 1, R is the position from the center of the particle, minus D would be 0 at the surface. I guess D is the radius, given this D. So when you get to the surface, it's 0. And then you get to 1 divided by that means you're at 1 layer of these little green beads. So you can kind of see the little green polymer beads, and he's got 2 layers there. So he's at 2. So he's got a bunching up of the nanoparticles separated by 2. Then as you increase concentration, they go to 1 and 2. And he says that this 1 and 2, so this is sum up the correlation function. So this is cumulative correlation function. So the integral of this, so it's got 2 steps to it because it's 2 peaks. Then when he gets to this Rm, which is the minimum here, he says that's the separation distance, like the 2 bead distance. So this ZR is kind of like how many segments are between are bonding the thing, like how many glue points there are between the 2 particles. And he's getting this from Prism, and he gets the Prism from the X-ray scattering data. So he does X-ray scattering data, and then from that he explains what he gets from it. He gets all these numbers from it. From the X-ray scattering, he feeds that into Prism. Prism generates a correlation function. They could have gotten straight from the X-ray scattering by Fourier transform. Just take the intensity and Fourier transform that, you get this thing. So, but he's taking the original data, feeding it into a simulation. getting this thing, and then he's getting this thickness of this layer here. Right. So his model is that these things are glued together by these beads, and then he's going to have. So it's a pretty simple model in a sense. Okay. All right. So this is the Arrhenius behavior, energy over KT, beta is 1 over KT. Right. So this is like typical, like viscosity would go with this. This it would be beta would be negative here. This should be negative, or energy is going to be negative. So, right. So decay with temperature, in other words, with an exponential. So the relaxation time is like viscosity times frequency. Right. So it's basically they have the same Arrhenius dependence. There's a prefactor that's a polymer, which would also be an Arrhenius behavior. Like the relaxation of the polymer is also like thermally activated. So this Arrhenius means you have an activation barrier. I talked about it before, like there's some kind of energy barrier you have to go over for the thing to happen. And in this case, the energy barrier is these beads kind of moving out of the way, I guess. Although he says no one knows what delta E is. So the purpose of this is to figure out what is delta E. Like, so he's going to calculate delta E with his prism so he can say what it is. So he's going to take the X-ray data, do prism to get the correlation function, use the correlation function to get delta E, and to get this NB, which is going to be how many of these monomer beads are between an average particle. And then because that all works, and this model is consistent with the data, then he has a model for what's happening with the nanoparticles. So there's a couple problems with that whole picture. One thing that becomes obvious later on if you look at the Yevitt paper. So he's got, this is his correlation function, and this is increasing concentration, right? 6, 16, 27 in Yevitt, and his is something similar to that. I don't know what it is. Right. So the position of the peak doesn't move, right? So that's kind of a problem because when you measure the X-ray scattering, the peak moves. The peak is the position of the particles kind of relative to each other, right? So as you increase concentration, they move in closer together, right? They have to move closer together because there's more of them. So when if they're dispersed and say they're separated by charge or whatever interaction, then as you add more, they get more crowded, they push together. So when they get together, the V gets smaller and the peak should move to the, let's see, actually this peak, yeah, so its higher concentration is green, so it moves to the right. So it gets a higher Q or a smaller distance. The concentration goes up, the spacing gets tighter. That's the way things behave, right, normally. So as you concentrate, so it's broad because they're randomly, kind of somewhat randomly, as the concentration goes up, they kind of crystallize. So then they reach a finite where they touch and they can't get any closer. And also it becomes like a perfect, like a crystallized perfect position. So it'd be a spike, it would just be a delta function. So it's going from a broad kind of amorphous halo to a delta function, and the size is getting smaller as you increase concentration. With the simulation, the size stays the same. Boom, 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 it's always the same size, right? So that's kind of weird. I mean, there's ways to dance around that. Like you say, I mean, so he can get around that by saying he has these clusters. So the only thing he's really measuring are these local individual things so that he's fixed. But if he considers all of them, then it would become like that. And then Yevitt's paper, they do that. Like they generate these moving peaks, you know, but in this paper, he just says it's fixed. So there it's fixed. It's just somewhat of a problem with it. Anyway, so what else is in here? We don't need this guy anymore. So anyway, so you take the correlation function, then you sum it, you integrate it, and you get this number, ZR. And then CR, so log of the correlation function, this is from statistical thermodynamics. So the log of the correlation function gives you the energy. This polymer mean, PMF is polymer mean, PMF, he defines it like right here. It's in the quiz too, I defined it there. Polymer mean force or something. It's defined it here. Potential of mean force. So it's a separation energy. So that's that potential of mean force. Oh, potential mean force is small w. It's related to big W. Let's see, it's explained in here. But big W comes from log of the correlation function. And it's right below this. It's big W's log of the correlation function from which one can determine small w because see, big W and small w are related. Energy is the small w. You need the small w. I don't remember how small w comes from big W. It's in this thing right here, I think. Anyway, from this sum of the correlation function, you get how many, because this correlation function is based on like how many, and then if you sum it up, you get how many beads are at that interface. So that this thing, when you reach this minimum of the correlation function for the two layer, that's how many are at the interface. So you can get this NB. So your delta E is going to depend on how many, and the small w you get from the big W. Someplace here. Let's see if I can find it. A lot of W's, 255, and the same number of big W's. What about space W? There's only 136 of those. All the widths. I think it's not finding any of the W's that I want. How many times does he use the word with? Oh, it's going to be after the small w shows up. Oh, big W is that thing. From which small w, but how? How do you get small w? It's in here somewhere. Maybe it's in one of the other papers. Oh wait, that was it. I just sit by it. Sit by it. Oh, it's circling back. Somehow you get small w from big W. Big W you get from the oh, he calculates big W from the correlation function. You get the energy, and then you plot. Oh, that's it. Okay, all right, I remember now. Right. So small w is the barrier energy, right? So it's good. You plot the energy as a function of that position thing. Then you find where the barrier is between the minimum and the maximum for this Rm, like at the Rm position. In other words, that's the barrier energy it has to go over to bind together. So it gets the W from that, from converting, taking the log of GR to get big W, and then plotting that energy versus the size and finding the barrier energy, delta small w. That's it. It's in the figure. But all right, so then you can calculate the whole thing. Like you have delta E, and then you can plug in delta E to get the thermal dependence of the relaxation time. Then you can measure this relaxation time at some kind of quasi-elastic neutron measurement, right? Or you can measure it from the viscosity. So that's the game he's playing in here. So he can play with everything then at that point, because he has all these are just parameters to feed into his prism, and then he spits out those other curves, and from the other curves he can plot everything against everything. So he can plot against loading, he can plot against the energy of the particle, the polymer, change that energy. So some of these would be like polyvinyl PVAC, polyvinyl acetate is 1. Then I think he does like, oh, he does here, PVAC, PMMA, P2VP. So this one's with the really strong interactions. This is weak interactions. So I think this one's 1, this one's 5, and that one's like 7 or something, or 6.8. Right, so he has these 3 experimental ones. They're reported in the literature by Yevitt, some other people. So he can compare the literature ones with his, right? So he can get his delta E value for different loadings for the different small epsilon NP values that he guesses match up with those polymers, like 3, 5, 6.8 for PVAC, PV2, and then the PMMA. Then he gets perfect match, like everything agrees. And if he divides from some arbitrary number, lambda, that changes with the polymer, he can get a universal curve, which everyone's trying to get a universal curve. Like take all this stuff. He can predict each curve. How do they relate to each other? They relate by this number lambda, which he doesn't know what lambda is, but he knows the values of these polymers. So one of the questions is like, what is lambda? That's kind of an open question. It could have to do with a lot of things. Basically, that you need this lambda to scale these delta E's to make them universal. So lambda increases, so lambda is 1, 2.1, and 5 for PVAC. PVAC is the bottom one, so it's 1, 2.1, and 5. So it isn't just like it would be, it's 2. If this was 3, then that would be 6.3, not 5. If it was just proportional. So it's not just proportional to the E number. So you can't just divide by E. So you have to divide by lambda. Lambda is different than E. So whatever lambda is, it's got something to do with E because they both are it's monotonic in E. So it's when lambda increases, E increases. So he does that with each of these. So for the first one, like how many are at that interface, as a function of loading, you get more at the interface as you increase the loading. And as a function of this energy, you get more at the interface with higher energy of interactions. That kind of makes sense. He plots it as log of, he plots this as, let's see, he makes a different plot of this. That isn't the same thing though. Ln of GC total. Tape bridge number. Log linear plot of contact value of GR versus theta. Anyway, these inset plots are supposed to universalize these plots. In other words, linearize or make them all fall on top of each other. So here, like if he takes this barrier energy for the peak and the energy plot, then if he subtracts from that the energy that he put in, they all fall in the same curve. And he explains why that happens. And then for this thing, he divides by lambda and he gets this universal curve. And he doesn't explain why that happens. So basically, he gives the values for lambda. And for this thing, he explains why this log of the G. So log of G, the correlation function, is supposed to give you Z. And Z at the peak gives you N. So somehow that makes sense. Like log of G gives you Z, and then you get N from the value of G, value of Z at the RM value. Anyway, this is a long and tedious thing you can look through with this for the homework, like figure out what he's talking about. I think it all more or less makes sense. The problems, so he's happy with that. That's kind of where this goes. There's a lot of background references for this thing. This is his supplemental, that's there too. So it shows like for the things he left out of the paper. So this is in a journal called Polymer News or something, macro letters. It's a pretty high citation index, but basically page limited. So it's limited to like 3 pages. So he puts up all the details in the supplemental. So everything he mentions back and forth, he mentions this supplemental. It's not a really long supplemental. What else? this is Sanat Kumar, the guy at Columbia, and Colby's, we've looked at Colby's stuff before, rheology, he's at Penn State. So mechanical reinforcement. So this is just saying, like, also about the bridging of this. He references this in this Schweitzer paper. So just saying that you can talk about this interface in terms of no bridges, which is the original McKay thing, just van der Waals interaction, and then rubbery bridge, which is what these people are talking about, and then glassy bridge, which I think is what Schweitzer's talking about. Like, it's this strongly bonded thing, and they've broken this into these regions. So, and that, like, they compare it with a viscometer measurement, right, to get the gel, sol, all the parts of this thing. This thing is, this is another thing looking at, so log AT would give you this delta E number. So it's kind of looking at how that changes with temperature. So at high temp, so it's 1 over T, so it's an Arrhenius plot of AT to get the slope would be the delta E. So at high temperatures, the polymer matrix dominates. At low temperatures, you get this combination of the matrix and the nanoparticle thing. So there's this transition region to this. He references this paper too. It's kind of important to his theory. This is a mixture of Chinese people and a guy at Michigan State. But, this is another paper on the same subject. I don't remember what this paper is. It's reference, so the pipe prism thing and this business. This one's nice because he actually does X-ray scattering, compares it with this correlation function. He gets in the same way using the prism thing, because Schweitzer's on this paper. See, Schweitzer's the lead, actually the contact author. Yeah, that's a rheologist doing the measurements and the X-ray scattering stuff.
Who's on that image up there in the top? Yeah, that one of the abstract.
Yeah.
Could the fact that that peak doesn't move position just be accounted for by the smaller secondary peaks as R increases? So, like, I don't know. So I guess is that S, is that the structure factor in that Sachs curve?
Yeah.
So I guess the
So this is the intensity divided by the dilute, like you get dilute particles.
right.
So you just get the correlations of the particles.
Right, like so the peak shifts right as you increase concentration. Also, as you increase concentration for the correlation function, your secondary peaks get smaller. Your primary peak, I guess, gets bigger. So could that reduction in the secondary peaks be related to the shift in the peak in your scattering curve? See what I'm saying?
Yeah. Well, there's a division, his division line in Schweitzer is like right here, because he says this is this glassy. And these things are something different. These are like from liquid. In other words, particles are floating around. So they're two separate things. So yes, it could be. Anything could possibly explain this. That could be one. He's got the liquid over here. The Sachs, I think. So I think that one is like the liquid, and this is his. So anyway, the thing is, like, what's missing here in the whole scheme is that the silica is charged at the surface. It's got a pretty heavy surface charge, and that's really the origin of this peak. I mean, it's a large part of the origin of the peak is a surface charge, which is completely ignored in this thing. I mean, explicitly. So he just has energy, polymer, energy, particle, energy, particle, polymer. It's got 3 energies, which is typical for any simulation. But one of the energies, the ionic energy is governed by the screening length, the device screening length. And the more particles you put in, the more ions you have. So the screening length gets smaller. So that the interaction between particle decreases with particle concentration. Because you're adding, as you add the silica, you're adding ions. The added ions decrease because the by screening length is going to go 1 over the ion concentration to the square root. right? So as you add more ions, the screen length gets smaller. That means there's less interaction between the particles and only happens at a smaller and smaller distance. That's not accounted for there. They don't think about that at all. So it's pretty simple what they're doing. They have these fixed energies. The energies aren't fixed with concentration. It's more complex.
I think I see what. I guess one more thing I just noticed. So like the peak of the green curve and the scattering data, it's at like 0.03 approximately. That lines up closer with a size of nearly like 21 nanometers. So the fact that the major peak is close to like 24 and you have,
Yeah.
I mean, it doesn't quite line up, but
No, it's close
guess-
enough. I mean, that's an approximation, right? So
yeah.
I mean, it's pretty close.
Yeah, I guess it's just like, so your dilute curves, you have the peaks across the board at the higher distances. They're
Average
larger,
out.
and so if your scattering curve is just an average of, I guess,
Right.
correlation function, basically, that sort of makes sense.
Yeah, that's a pretty good argument. I think that's kind of, you could read this paper and that's kind of what the argument he makes, more or less. He only shows this in the graphical abstract, Also, another weird thing is that I've never seen this before. He refers to the graphical abstract in the abstract. Like he says, he says like somewhere he says the figure to the right, in this abstract. I never seen someone refer to this thing in that, Like I always thought those were supposed to be separate, but I think it's in this one. Anyway, maybe it's in this. So yeah, you can look through what he says. I mean, it might be useful, and it's the same authors. It's like 2020, and this is 2022. So they should know what they wrote in their own paper. So he's using the same thing, prism. You can see it's like the hammer thing. So you talk about the hammer, it's a nice hammer, it's shiny. We're going to hit this nail. Everything's a nail. So it's pretty typical, like they're going to just make papers out of this hammer thing they made. And this is going on since '87, right? So it's a pretty useful hammer. It's like a whole career, not just on this kind of thing, but in all. Basically, it started just polymer blends. Now it's nanocomposites. Next it will be whatever. They've done interfaces. They've done a lot of different things. Anyway, at some point he gets, I think this is the simulated scattering curve, and he gets the shift in the peak, right? Same thing, correlation function, corresponding collective structure factors. So collective is probably the key word here. So yeah, he gets the shift somehow. So I think it's by some kind of summing up the things. I didn't actually read this one all the way through it. The Yevit papers are a lot harder to access than the 5-page Schweitzer thing. Although I like this, the graphics are nice. This is a pretty useful graphic. So anyway, so that's one of the issues. What else is in this thing? It's just like describe the Arrhenius. Is it appropriate here? These can always be debated, whether it's appropriate or not. It should be appropriate. What is RMs? You have to go through how he describes those plots. Show interesting nonlinear behavior. Why does it behave the way it does? Stuff. You have to look at the paper. How do you measure delta E experimentally? That's a good question. So he says how to get it. But basically, delta E is the thermal dependence, right? So this is the thermal dependence of the relaxation time, which could be just measure the viscosity at different temperatures. And then if you run the polymer one, you can kind of get the Rio, the nanocomposite divided by polymer, then you just have this thing left over. And then if you do a temperature series, delta E is the slope in temperature. I could do log of that ratio versus beta is 1 over temperature, you should get the slope would be delta E. Right, so you just get it from viscosity measurement at different temperatures. He says in here you need 2 temperatures to get it. So that's how they get it.
Question, sorry, the Rio T, I understand. What's he saying if the tau sub poly is?
That's the polymer without the filler.
Okay, sorry.
Just, yeah, so you have kind of, think of this as the viscosity. So it's just the viscosity of the filled nanocomposite, the viscosity of the polymer, the ratio of those two, log of the ratio of the two versus 1 over T. That's an Arrhenius plot. The slope gives you delta E. There should be a negative delta E. I'm not sure he shows that. He shows that, maybe he shows that in the supplemental somewhere. Right. Should. This is,
There was the beta delta E, but very, very bottom. So the very bottom of the
yeah, that's just his result, right? That's the same.
no,
result.
like there's like all the way down right before the.
This is like scaling factors will
That's
collapse.
the gamma or the lambda.
Yeah, that's a lambda, right? Yeah, so lambda's, he doesn't even speculate, I think, what lambda is. So that means you can speculate. I think he shows, well, it's just a viscosity measurement. This is the AT is a shift factor, right? So the AT is how you combine different temperature for the frequency scan at one temperature and frequency at another. Going to combine the viscosity so you scale them. AT is the scaling factor. So the AT is basically the viscosity temperature dependence. If you take this one number of how the two match up with BAT, that's the difference in viscosity. So log of AT gives E. The slope of this is delta E versus 1 over T from the just using the shift factor to get it. So he measures, in other words, he could measure at one frequency and then just get then plot the viscosities of those frequencies, or you can take the frequencies and where they overlap, slide them to match, and then take that shift factors based on more than one point, right? So it's a better number than just taking 1 point. So he takes that AT ratio, AT0 would be the polymer, AT would be the nanocomposite, log of that versus 1 over T, and the slope is going to give him this delta E over K. Right? So he's got, so the fact that these are linear means that he's got a delta E for those. He has it for the 3 polymers here. That's called an Arrhenius plot, right? Anytime you see log of something, it's 1 over T, that's Arrhenius. And the thing you get out of it is the energy, slope. The slope will be the energy. So yeah, he's got the thing here, the equation. So he explains how to get it here. And then the thing about the peaks not matching up. And then, all right, so this is thing, the packing factor. So if you have a perfect hexagonal HCP or FCC perfect crystal, that's the densest you can pack things. That's like 0.72, I think. So it's 0.72. So, and then in this field, so this becomes important in understanding this stuff because that's your idealized situation when you get the particles, the nanoparticles all together, how dense could they possibly pack? Then people talk about, in some of the papers, they talk about like an amorphous maximum packing factor, so it doesn't crystallize. And that number is usually 0.62 instead of 0.72. And in this paper, he uses this number as 0.6, which is just because the 0.62 is just made up, so he's using something simpler. Right? So this MT is the packing factor, and that has something to do with in the Yavet paper, he talks about using eta T in the calculation to get this thing to shift right. Like he has eta n, the packing, this is the concentration of the particles, and then eta t is the maximum concentration that you could have kind of in a local region if they perfectly packed. And somehow that leads into the shifting of the thing. He didn't invent this. This is around in the literature for the stuff. You can use this eta t to fix things. Here, so he has a way to calculate it. So sigma is the particle, the bead size of the polymer. D is the size of the nanoparticle. And they always use in spheres. And then rho, this is the density of the polymer, density of the nanoparticle, and somehow you get this packing fraction from that. It's a geometric number. Then he uses that somewhere in here. This is we didn't go through this. Maybe we mentioned it, right? But this is just the Zernicke function for correlations. Right? So you have the structure, local structure, and then the long range structure. So omega is the local structure, and then this H is the long range structure. And the local depends on the, so the local depends on the long range. The long range depends on the local and the long range. So it depends on itself. So it's a recursive formula. It's the only way to solve a recursive formula is by using a closure equation, like a connection equation to relate the two. Because if it's defined in terms of itself, you can never find it. Because every time you move that, this thing moves. Right? So you don't have a solution. So you need to guess something. And the thing you guess is called this Verlet closure. That's what he says, like, we just invented this modified, I don't know what it is, modified Verlet closure. It's just a function that gives you the correlation function. So it's basically an empirical equation they put in, I think, that gives you the solution to a structure factor. Because otherwise it's recursive. This thing's recursive, so you can't solve it. So, see, things get dicey when you talk about correlations. That's the rule of the game. Like, and at some point, nobody really understands what's going on. I think that's a general rule because it gets too complicated.
That was us in statistical thermo last semester.
Yeah, I mean, you got to understand that nobody at all, no one, even Yevik or whatever, didn't understand what's going on here. Because the reason that it's complicated, and the reason you need the equation is because it's too complicated to understand. It's like there's not gonna be a simple answer to this thing. I mean, so the simpler you come out with, the better. Supposedly, with this kind of thing, you have to decide like what do you need to solve your problem, to model your system. Like, and what you need is absolutely the simplest possible answer. Right, because everything else, you don't understand what's going on, but if it's simpler, at least it's going to be something you can handle, And all these more complicated things, people are throwing in like monkey wrenches. So throwing in something to fix something it's empirical. So it's not going to help unless you need it, then you should use it. But if you don't, then you should, So kind of the theme. And this prism is dealing with this by integrating overall interactions of things. So it's an integral form to solve this thing. I don't really understand the prism approach. It's just a computer program people use to spit out. And it's based on something this guy Chandler did at Berkeley back in the 60s, for low molecular weight structure factors for low molecular weight like toluene or something. And then to extend that onto polymers, that's what Curl and Schweitzer did. So I think Chandler won the Nobel Prize or something. I don't think he won the Nobel Prize, but he essentially did for this kind of work for low molecular fluids. And then these guys became famous in polymers for doing this. I think they might have won the Ford Prize in polymer physics or something for doing this kind of understanding by this integral approach. And then a lot of people use this now. I don't think it's included in some packages, like simulation packages, like Prism. So in a sense, it's just giving you like the correlation function. It's just a way to get a correlation function for polymers. And everyone agrees that it works, so that's kind of a useful part of it. Understanding that, I don't think that it's like that people understand it that well. The other thing, you also see one other thing that's like this volume fraction thing that you see in these papers. It's like the cube root of, he gives that in here somewhere. Anyway, there's another function that you see through all these papers. It's like the cube root of the volume fraction gives you the spacing. That's why this equation reminds me of that. That's not the equation. Anyway, they use it. I think both these papers use that to estimate the spacing at some point between the particles. It's a volumetric spacing. Oh yeah, it's in the other paper. It's in the parent paper here. And it's at the beginning, I think. Like the simpler paper is going to use that. Just take the volume and then the cube root. It's in here somewhere. It's in this paper. Okay, paper. Because McKay uses that. Where?
Bottom of the lower right column on that page. There it is.
Oh, yeah. Yeah, this thing. Yeah, so I could have asked you to derive that. I haven't actually been able to derive it myself, so but that would be a good thing to be able to derive. Everyone uses that to get the spacing thing. So anyway, I don't know exactly where. It's just a geometric thing. The cube root is like 3D to 1D to get the spacing, but I don't exactly know how that function came out. Anyway, that's in here too. That's in all the papers where they're just talking about general correlations of particles. So that's kind of a useful function, but that's about it, I guess. You know, so if you, yeah, whenever you want to turn that in, it's good. You know, Friday is like the last day, but I'm not sure when I'll turn the grades in. But I don't think it'll matter. I might turn in the grades right away, in fact, you know, but you don't just turn in the grades. But so it'd be good to get that. It'd be good to get the comments on the course. You know.
Not a Nobel Prize, but it's the ACS Irving Langmuir Prize.
Oh, okay. Chandler?
Yeah.
Yeah, all right. That's a pretty good prize. Yeah, the Langmuir Prize.
First recipient was Linus Pauling, you know.
Yeah,
Never-
that's a
think I
pretty
ever heard of
solid
him.
prize. Yeah. Yeah, Chandler's like really well known like that. I mean, yeah. They kind of just took what he did. Like, I think, way I understand it, they didn't do that much to change it for polymers. They glued them together, you know, I think. But anyway, they got pretty famous for that work.
So it's like another what, Rouse situation.
Kind of, yeah.
It's like, hey, I got this.
I mean,
math that
Kuro, they're
works.
both nice people, but Kuro is like an excellent person, you know, a really nice person. And Schweitzer was a little bit more aggressive. And he went on to like Illinois, like professor at Illinois. Kuro like retired at Sandia and is living outside of the mountain now. So it's like, I think Kuro's happier you know, between them two. But,
Thank you very much.
Yeah,
Enjoyed the
thanks,
class.
Yeah,
Thanks, yeah.
thanks for a good semester.
yeah, thanks you guys. Hmm.